This is lesson 34, and this is dealing with summation notation. What we're going to be talking about here is the Greek letter sigma. Now, we already have a lot of other Greek letters that we use when we're dealing with math. For instance, pi, it stands in for the irrational number of 3.14 continuation. But this sigma is allowing us to do a function. It's telling us to do an operation. So the Greek letter sigma looks like this. And what we're going to do is identify each one of the different parts of this problem. The first one is, this is called a typical element. This is what I want to actually substitute these into. This is my lowest value, and this is the highest value that I'm going to put in. So since I count 1, 2, 3, 4, which is really easy to do, I'm going to say I'm going to put in every value of y in for y starting at 1. So I'm going to use 1 squared plus 2 squared plus 3 squared plus 4 squared. The summation is telling me I'm adding every element from 1 up to 4. So it includes 1, and then 2 squared 4, 3 squared 9, 4 squared 16, 1 plus 4 plus 9 plus 16 is 30. So this is the smallest element all the way to the largest element. And I simply substitute those in. Now there's some times in this problem that there's some things I have to be careful of. If I change this problem up a little bit, and I leave that as my smallest and my largest, but I put another value in, for instance, if I put an a here, this was going to change my overall summation, but not by very much, because my typical element is still y squared. The a is a constant value. So I'm going to go ahead and leave that constant value. I'm not going to count that up. I'm going to change this even further, putting a 3. My first element would be 1, so I'm going to say 3 times 1 squared times a, plus 3 times 2 squared times a, plus 3 times 3 squared times a, and then plus 4 times 4, I'm sorry, my mistake here, this is still not changed, 3 times 4 squared a. And this is going to work out very similarly. I would end up doing 1 squared, which is 1, times 3, which is 3 times a and 3a, and I continue the same thing. Notice that the a did not change as it's part of my typical element, and then the 3 did not change as it's also part of it. I only substituted in for the variable that I'm using. That leads to the question, what happens if I had a problem that was similar to this, but didn't have an a in it, or a y in it, I'm sorry. Well, in this type of problem, I'm going to assume that the y is there, but it's just brought to the 0 power, because I could substitute this in and just say y to the 0, which would be the same thing as 1, which is allowed because it's just 3. And then I'm going to plug in every value of y. So I'm going to say 3 times 1 to the 0 power, plus 3 times 2 to the 0 power, plus 3 times 3 to the 0 power, plus 3 times 4 to the 0 power. And this is going to say, well, 1 to the 0 power is 1, so this becomes 3 plus 3 plus 3 plus 3. And so this is going to have 4 3's, 1, 2, 3, and 4, as it goes through. Notice that even though this number went up, anything brought to the 0 power is still 1 and does not change my typical element. So anytime you have the typical element variable inside of my summation problem like this, but it's not represented here as a typical element, I immediately assume it means that this number is here. It's just hidden as a 0 exponent, and I work it out that way. I can do this with fractions. I can do summations. For instance, if this was 1 over y, okay, what I would do is just put this would be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and then I would add those up as well. So the summation notation allows me to just substitute in this value starting here all the way to here. And this number can go as high as we want or as low as we want, and these are the limitations of the summation itself.